This is part 2 of a multi-part series for a scenario involving internal flooding. The scene involves 3 rooms: the top room where the pipe break originates, the stable room where the water leaks under the door first, and then onto the bottom floor. In part 1, we learned how to couple a static model based on Torricelli's law in the top room to create particles which are used to simulate the hydrodynamic conditions in the stable room. Now, let's continue where we left off on part 1. In this tutorial, we will perform hydrodynamic analysis on both top room and the bottom room. So let's just use the file we have created so far in part 1, which is indicated by the link. So let me pause here while I give you time to gather these files and prepare the neutrino file which we loaded from part 1. Let's just load the neutrino file we created in part 1, and once you load it in neutrino, the file looks like this. Let's hide the top floor and create and position what we call as a flow emitter. In the flow emitter, let's change the position. Once we change the position, we would want to place it where the pipe break actually happens. And we can also change the scale of the flow emitter to match roughly the area which is indicated by the pipe break. Let's change some of the other parameters. Let's change it to the magnitude of the flow in the normal direction, which is the speed setting option in the flow setting, and then set the flow rate to 0.5. Let's create 2 measurement field nodes. These measurement field nodes can be created in the scene builder. The scene builder can be opened by window and scene builder. And once we create those measurement fields, the first measurement field, let's adjust the position. Position one measurement field right in front of the door and position the other one right behind it. Let's change the size of these measurement fields to match roughly the size of the door itself. So the width and the height would match the door. So the second measurement field, we give this positions. So you can give these same positions in your file. The measurement field node 2 is the one which is on the stable side, which is measurement field 2, and measurement field 1 is the one which is on the other side, which is behind the door, in which the pipe break actually happens. So the node graph window has got all the nodes in the scene, and their inputs and outputs types are color coded with their appropriate colors. Let's find the right 2 measurement fields nodes and try to move them around so they're a little bit more legible in the node graph editor, and also see the Torricelli source. Let's connect the measurement field 1's KIO fluid height to the Torricelli source KIO fluid height, and connect the measurement field 2's KIO hydrostatic pressure to the Torricelli source K hydrostatic pressure. Now let's create a flow killer node. The flow killer node is a node which, as you know, kills particles, and position this flow killer right behind the door in the top room. So we want to kill the particles which are moving into the door, and we want to collect these particles and then create new particles on the other side of the door. So we need to position this killer and make some connections first. So position the flow killer right behind the door in the top room. Adjust its size to match that of the door gap. So we're going to use this as almost a transporter, and we're going to create an emitter connected to this killer on the other side. Then there's one more final set of connections to make. First, let's make use of an alternate way to make connections so that you're familiar with both ways. This connection editor can be popped open from Windows in Connection Editor. When you select the Torricelli source, you can press Load Source to load it on the left, and then load the killer on Load Target on the right, and connect the KIO num particles, then connect the KIO num particles from the Torricelli source to the killer side. Then press connect. Okay, All this is done so that the door gap can be smaller than the particle size as the particles are transported across. Now we're ready to simulate. Arm the simulation and simulate. And you can see the flow from the flow source accumulate near the door, and when it reaches a certain threshold corresponding to the gap being filled with the flow from the particles killed on one side, they transport it into the other room. Now at some point the accumulation would reach quite high and perhaps the door fails and the entire flow spills over into the stable room. Let's have a look at how it's done in the next tutorial, but in the meantime, let's just have a look at the simulation. Thank you.